Okay, so last class we discussed your work energy method, right? Today we'll discuss your virtual work method. I'm sharing my screen. Is the screen is visible? Or
The method of virtual work. In previous lectures, the work energy
please mute yourself. Okay, if any participant is mute yourself. Just text me in the chat box. Okay.
principle. The method of virtual work. In previous lectures, the work energy principle was used to relate external work to internal energy in a structure. See lectures Essay 19 and Essay 20. For example, for a
Let me share once again.
simply supported the method of virtual work. In previous lectures, the work energy principle.
Just give me a minute. Am I audible? Please type in the chat box. Am I audible? Okay, okay. I'm playing the video. Okay, let me know if it is the audio and video is okay or not.
The method of virtual work. In previous lectures, the work energy principle was used to relate external work to internal energy in a structure. See lectures SA 19 and SA 20. For example, for a simply supported beam subjected to a concentrated load, the work energy equation can be written as 1/2 P times delta equals to 1/2 times the integral of m. The method of virtual work. In previous lectures, the work energy principle was used to relate external work to internal energy in a structure. See lectures SA 19 and SA 20. For example, for a simply supported beam,
So at first it is reviewing the earlier method we have seen, work energy method. Okay, then we'll move to the virtual work method.
subjected to a concentrated load, the work energy equation can be written as 1/2 P times delta equals to 1/2 times the integral of m times d theta. The left side of the equation represents external work done by the load. The right side of the equation represents the resulting internal energy stored in the beam. On the left side, P is the applied load and delta is displacement under the load. On the right side, m is bending moment in the beam and theta is slope of the elastic curve, both due to the beam's deformation. We can use this equation to calculate delta, the displacement under the load, as was demonstrated in lecture SA 20. The work energy principle can also be used for trusses. For example, in the case of a simple truss like this, we can write 1/2 P times delta equals the sum of Fi delta I over 2. Again, here,
So it says that we can use work energy principle for truss also. We can use a work energy principle for truss, for beam and frames. Okay, so we'll discuss mainly about truss and beams because we have studied how to find the deflection in beams. Now we can find the deflection in truss also by equating external forces equals to internal energy. Okay, this shows half P into the deflection is equals to summation of all the internal energy. Fi, that means force in one member. See, I is represented from, I is designated from 1 to 5 because here 5 members. So you can replace 5 F1 delta 1, that is force in the member 1, deflection in the member 1. Okay, F2 del 2, force in the member 2, deflection in the member 2. F3 delta 3, force in the member 3, like this in this, or deflection in the 3. Okay, summation of all divided by 2, that will be equal to your external energy, which is half P delta. Okay.
the left side of the equation represents external work and the right side represents internal energy. On the left side, P is the applied load and delta is the horizontal displacement under the load. Fi is the axial force in member I and delta I is the elongation of the member. So, if we were interested in calculating the horizontal displacement at C, we could write delta equals to the sum of Fi delta I over P. Since the truss is statically determinate, we can easily calculate member forces and elongations as was demonstrated in lecture SA 19. But what if we needed to calculate vertical displacement at B? Since delta B does not appear in the work energy equation, we cannot solve for it using the work energy principle. We need to use a more general method, like the virtual work method, to accomplish this. The method of virtual work is based on the work energy principle, but can be used to calculate displacement at any arbitrary point in the structure.
Basic difference between work energy method and virtual work method. In virtual work method, we can find the displacement at any arbitrary point. Okay, at any point of the structure, we can find the deflection. But work energy method, we cannot find the deflection at any arbitrary point. Okay, that is the basic difference. By this method, we can find the deflection at any arbitrary point. Got my point? The main difference between the two methods is we can find the deflection at any arbitrary point by this virtual work method. Okay, let's
Let's start by examining the basis of the method. Suppose we have a structure subjected to a set of external loads. Consequently, the structure is going to displace like this.
I have been given a truss. Okay, I have been given a truss and a load is applied at C. So when I apply a load at C, it will get deflected like this. Okay.
Let's refer to the horizontal displacement under P as delta H and call the vertical displacement under load Q delta V.
So due to this P, it is considering the horizontal displacement at delta H and vertical displacement as delta V.
Now suppose we add an imaginary vertical load to point B. Since this load, here denoted by P star, is imaginary, we'll call it a virtual load.
So what we do in a virtual method, we place an imaginary load on the point where we were asked to find the deflection. Okay, so if I ask to find the deflection at Q, I'll apply an imaginary load at this point. Okay, virtual means what? It is virtually present, right? So I'll apply a virtual load at this point. At this point, if I have been asked to find a deflection at B. Okay. And P star is represented by the imaginary load.
The structure can be easily analyzed under P star in order to determine the virtual member forces. Let's refer to these forces as F star 1, F star 2, and so on. Since there are 5 members in the truss, there are 5 virtual member forces. Note that P star is applied in the direction of delta V. Since this imaginary load travels through the real displacement, it does imaginary or virtual work. The work done equals P star times delta V. We call this an external virtual work since it is done by an external virtual load. Since the real loads, P and Q, cause real member deformations, then it is also true that the virtual load causes internal virtual work. For member 1, internal virtual work equals F star 1 times delta 1.
So it says that as I'm applying a virtual load externally, so it will give a work P into delta. So due to this external virtual work, there will be some internal virtual work also. Okay.
Where F star 1 is the virtual member force due to P star, and delta 1 is the real elongation of the member due to P and Q. Similarly, for member 2, internal virtual work can be written as F star 2 times delta 2. So in this case, the total internal virtual work equals. The principle of virtual work states that external virtual work equals to the internal virtual work, or now, since P star is imaginary, we can give it any value we wish. To simplify our calculations, let's make it a unit load. So we get delta V equals the sum of F star I times delta I. Here, delta I is the real elongation in member I due to real loads, and F star I is the internal force in the member due to a unit virtual load. Using the equation, we can easily calculate delta V, the vertical deflection at B, due to the real loads. In fact, using this method, we can calculate displacement at any truss joint. For example, to calculate horizontal displacement at D, we place a horizontal unit virtual load at D, and we calculate member forces due to the load. Then, horizontal displacement at.
So what we will do, we'll place a virtual load at a point where we have been asked to find the displacement or the slope in beam slope in trusses deflection. So if I have been asked to find out the deflection at D point, what I'll do, I'll place a virtual load, and due to that load, what will be the force member, I'll calculate. Understood? Suppose I have been asked to find the deflection at A. So I'll apply a virtual load at A, and I'll find the forces in other members due to this load. Understood? What I'll do, at any point, suppose at B, at A, at D, at C, anywhere, I have been asked to find the displacement. What I'll do, I'll apply a virtual load of 1 Newton at that point, and I'll find the forces due to this load on other members. Okay?
At D equals to the sum of F star I times delta I, where F star I is the virtual force in member I due to the unit virtual load at D, and delta I is the elongation of the member due to the real loads. Let's work through an example to better illustrate the method. Consider the following truss structure. The members are made of structural steel with a modulus of elasticity of 200 gigapascal. All the members have the same cross-sectional area, 20 squared centimeters. The truss is subjected to 2 concentrated loads as shown. We wish to determine horizontal displacement at C, vertical displacement at B, and horizontal displacement at D. We can start by calculating member forces in the... We wish to determine...
So, this is my question. Okay. Let me add student. So, this is my question. I have been given a truss member 5 mm. The member distance is 5 meter, 5 meter, and the height is 7 meter. Okay. Then a concentrated load, or you can say point load, is applied at at C, which is 500 Newton, and a point load is applied at B, which is of 200 Newton. And the elasticity, modulus of elasticity, E value is 200 gigapascal. You can convert it into Newton per mm square, and then cross-sectional area. That means the area of these steel tubes is same for the whole section. So this all the truss is made up of same material. Okay, and the cross-sectional area is same for all the members. AC, AB, BD, CD, all the members have same cross-sectional area of 20 centimeters square. Okay.
Horizontal displacement at C, vertical displacement at B, and horizontal displacement at D.
So we have been asked horizontal displacement at C, horizontal displacement at D, and vertical displacement at B. That is our question. We have been asked to find out the horizontal displacement at C, horizontal displacement at D, and vertical displacement at B.
We can start by calculating member forces in the structure. This can be done easily since the truss...
So first step will be to find out the member forces in the truss member, and you can find the forces in truss member by the method of joints or the method of sections also, right? First find out the reaction, then hope you remember. So recall from your last classes how to find out the member forces in these members of a truss. That will be the first step.
Is statically determinate. The support reactions are AX equals 500 newtons, AY equals negative 250 newtons, and DY equals 450 newtons.
So by using equilibrium equations, summation of all the vertical forces equals to 0, summation of all the horizontal forces equals to 0, summation of moment about a point equals to 0. So by using 3 equilibrium equations, they have found out the value of AX, AY and DY, because these are the external reactions. So they have found out 500, 250, 450. Okay.
The member forces are F1 equals 307 newtons, F2 equals 321 newtons,
So they have drawn a free body diagram of all the joints A, then B, C and D, and they will find out the F1, F2. Like if I give numbering like this, Let me change the color. So F1, F2, F3, F4, sorry, and 5. So by using method of joints, considering all the joints A, B, D, C, they have found out the value of F1, F2, F3, F4, F5. So the first step will be to find out the force members in the truss. Okay.
F3 equals 200 newtons, F4 equals 321 newtons, F5 equals negative 553 newtons. Now,
So you have to clear with the method of joints, how to find out the forces members in a truss. Okay, very important. See, everything is related in this subject. So please revise your earlier classes. Okay.
let's determine the axial elongation of each member due to the real loads. According to Hooke's law, axial stress equals to modulus of elasticity of the material times axial strain.
So what Hooke's law says that Hooke's law says that your stress is directly proportional to strain, and when you remove the strain, as per Hooke's law, stress is directly proportional to strain, and when you remove this directly proportional, stress is equals to capital E strain. And what is this E? Young's modulus or modulus of elasticity. Okay.
Axial stress equals axial force divided by the cross-sectional area of the member.
And what is stress? Stress can be found out force per unit area. And your strain is change in length by original length. So what we have been asked? We have been asked change in length. So we'll derive the formula for change in length. Okay.
And axial strain equals to the member elongation divided by its length. Therefore, we can determine axial elongation of each member using equation FL over EA. For member 1, axial elongation can be written as delta 1 equals F1 L1 over EA. We calculated F1 to be 307 newtons. L1, length of member 1, is 8.6 meters. E, modulus of elasticity of steel, is 200 times 10 to the power.
E and A values are given to you. Okay. Force you have been found from method of joints. F1 is force in the member 1, just 307. The length is 8.6 meter and E and A value is given to you. How 8.6 meter? This was given 5 and this was given 7. So by Pythagoras theorem, you can find out this length, which is 8.6 meter. E value is given to you, which is 210 to the power 9. They have converted into Newton per mm square. Then the area is given in centimeter square, so they converted into meter. Okay.
9 newtons per squared meters. And the member's cross-sectional area is 20 times 10 to the power negative 4 squared meters. So we get 6.6 times 10 to the power negative 6 meter for delta 1. We calculate the elongation of each of the remaining members in the same manner. Delta 2 equals 4 times 10 to the negative 6 meter. Delta 3 equals 3.5 times 10 to the power negative 6 meter. Delta 4 equals delta 2, which we calculated to be 4 times 10 to the negative 6 meter. And delta 5 equals negative 12 times 10 to the negative 6 meter. The negative sign indicates that the member actually shortens. It is in compression. Now that we have determined the elongation for each member due to the real loads, we can start calculating the desired displacements using the method of virtual work. To determine horizontal displacement at point C, place a virtual unit load in the direction of the displacement at C. Now determine the member forces due to this load. A simple truss analysis gives us the following virtual member forces. A negative force value indicates the member is in compression. The external virtual work for this truss is 1 times delta. The internal virtual work equals to the sum of F star I times delta I. This gives us So we can write external virtual work equals to internal virtual work, or 1 times delta equals 20 times 10 to the power negative 6. Therefore, horizontal displacement at B equals 0.02 millimeter. To determine vertical displacement at B, place a unit virtual load in the vertical direction at B and determine the resulting member forces. So the internal virtual work equals 9.67 times 10 to the power negative 6. The virtual work equation then becomes 1 times delta equals 9.67 times 10 to negative 6, where delta is the vertical displacement at B. So delta equals 0.00967 millimeter. Finally, to determine horizontal displacement at D, place a virtual unit load at D in the horizontal direction. The analysis of this truss gives us the following member forces. Therefore, the expression for internal virtual work can be written as, then the horizontal displacement at D equals 0.008 millimeter. We are going to examine the use of the virtual work method for calculating beam displacements in the next lecture.
So you can start, you can take a screenshot and you can try this problem, okay? So in the next class, you'll see for the virtual work method for beams, okay? All of you can write your roll number in the text chat box. In the next class, we'll discuss the virtual work method for the beam. Am I audible? You can write your roll numbers in the chat box. All of you wrote the roll number? Seventy-four, 100, 92, 51, 109, 106, 97, 90, 87, 82, 120, 103, 99, 61, 63, 75, 115, 76, 118, 84, 112, 81, 83, 94, 73, 114, 101, 91, 67, 98, 66, 119, 93. Anyone left to write? Last, Rohini Das, 93, 86. Okay. Anyone left? So I'll put a message in the chat box. So join that class. Okay. Anyone left to join? Write their roll number. Okay. So then in the next class we'll see the virtual work method for a beam. Okay. Thank you.